that would be inconvenient indeed if it couldn't focus. So basically what we did last time was, just the very basics and beginnings of convex optimization. We'll need a bit more of optimization this time, just because at the end of the day, for a lot of the problems that we're going to study, optimization is essentially the basic engine to really get our hands on the parameters. There will be another basic engine which is basically sampling, but we'll do that a little bit later. Okay. So those of you who've taken a convex optimization class, for those, most of it will be fairly straightforward. There will be a few new parts in it, but most of it will be straightforward. Who went to John Langford's talk this afternoon? Okay, a few. Okay, so this would have shown you a fairly highly optimized parallel convex solver and a few bits and pieces that sit on top of that. And so that might give you an idea a little bit more of how some of those tools are being used actually in a practical industrial setting. It's not the only tool that's being used in that context, but it would have given you a bit of a glimpse of what happens there. So before we move on with other solvers, let me just quickly show you a bit of conjugate gradient descent. And the reason why you would care about this is because if you think about the Newton method, it's actually really expensive, right? Because the Newton method basically requires that at some point you compute this Hessian matrix, and you compute the inverse, or at least you solve a linear system. So basically you have a system of the form, matrix times x equals y, and you want to get your hands on x. Mind you, it's typically much cheaper to solve for x directly as opposed to first compute the matrix inverse and do the other operations. And conjugate gradient descent is one of those methods that will actually help you do this. So let's just start out with the simplest case where we have just some quadratic function x transpose kx minus L transpose x that we want to solve. And well, obviously by just looking at that function, you'll see that x equals k inverse L will do the trick. Right? You just take the derivative, you invert k, and let's assume that k is positive definite, so things are all right. Now, what you could easily do if k were just a diagonal matrix, possibly just the identity matrix, it's very easy to get your hands on x. I mean, you just said x equals L. In general, that's not the case, but what you can do is, if you have vectors that are orthogonal with respect to this quadratic matrix K, you can basically perform an orthonormal basis expansion, except that rather than using the standard Euclidean identity metric, we use the metric endowed on the space by K. That's essentially the trick. So it's just that things are now orthogonal in a slightly different space than before. So more specifically, what I'm saying is two vectors x and x prime are K orthogonal if their inner product with K in the middle is 0. And the good thing is that m mutually K orthogonal vectors form a basis, and therefore they allow us a certain expansion and also allow us to solve a linear system of equations. And we're going to actually prove this. And if you think about it, this is really the same thing as what you would have in an orthogonal series expansion, right? So in an orthogonal series expansion, you get something of the form, my vector x is given by inner product between some vectors vi and x times vi. And that works as long as these vi's are all orthogonal to each other and they have all unit length. Then I can just sum over all the i's and I can reconstruct things. Now here, those vi's aren't going to be quite orthogonal anymore, but they're going to be k orthogonal. So let's prove that this is actually a sensible thing to do. So the first thing we need to show is that those vectors are actually linearly independent. Well, let's assume those y's were linearly dependent. So I can write 0 equals, well, k times these guys, and I can multiply it by some other xj. That's something I can always do. And now at this point, the only term that survives is xj transpose k xj times alpha j, right? Because all the other terms were k orthogonal. Now, this can vanish only if alpha j is 0 or the first term is 0. Now the first term can't be 0 because this is positive definite, and these are non-zero vectors, so by that I've shown linear independence. For the reconstruction, well, again, since we have linear independence, I can just multiply my reconstruction. So first of all, I can write z as a linear combination of those alpha xi's. They form the basis. So I can just, compute the inner product between some xj transpose k and z, and plug the expansion in here. Again, by k orthogonality, I find out that this allows me to get my hands on alpha j and on none of the other terms. And so then I can just solve for alpha j, and I get that this is basically xj transpose kz divided by xj transpose k xj. And then, for the linear system solver, you just plug that solution back in. And the good thing is that this is usually the thing that we observe, namely k times z. And we want to get our hands on z again. You had a question?
So I was confused, what is z here?
So z is the variable that we want to estimate. And, well, so if okay, let me just write out exactly what that then means. So if we have y equals k times z, then I can of course solve for z being k inverse y. Right? Now if I don't really want to explicitly compute this, I can just go and plug into this here, well, sum over alpha I xi. Right? Because it's a basis, I can do that. I can then multiply the entire left-hand side of this by some zj, with some xj, and here we have xj. So here we get, xj times k times these guys xi, which yields alpha j times xj transposed k xj. Okay? And now I can go and just solve, because I get then that alpha j equals appropriate is xj transpose y divided by xj transpose k xj. So this basically makes all the x's unit length. That's effectively what's happening now in this space distorted by k. So that's all very nice, but we don't really have this linear system of vectors x, so how can we get it? So what we really need is we need those vectors x. We need a way to orthogonalize these vectors as we go along, and how do we actually get them in the first place? After all, we have a lot of freedom in selecting them. Now, obviously, what happens is that these vectors really widen the space. So, because if you think about this problem here, 1/2 x transpose x minus L transpose x plus c has obviously this trivial solution x equals L. And what conjugate gradient does is it automatically, it's basically a Gram-Schmidt orthogonalization procedure that I do iteratively as I go through the data. Who has seen conjugate gradient before? Okay, that's actually fewer than I had thought. Okay, so this is actually new for some in the audience. That's good. It's a useful procedure to use on a single machine. This is not something, by the way, you want to use on many machines, but for a single machine this is actually an extremely useful strategy, because quite often what happens is that this matrix K that we're playing with only has a handful of really meaningful eigenvalues. And what one can show, and we're not going to go into details here for that, conjugate gradient basically zooms in on the significant eigenvalues first, and in the space where the eigenvalues are really small, it doesn't really do much. So therefore, rather than having to do a full matrix inversion, you will be able to find an approximately very good solution after only a few matrix vector multiplications. So it's a method to dramatically accelerate solution of a linear system if the system happens to be particularly easy. Okay, so how do we do it? So let's, for the moment, just look at these iterations here. So what I'm doing is I have this function here, f, and I go and compute the gradient at each step. So that's by kx minus L. I initialize x naught and v naught to be g naught is k times x naught minus L, and I set the counter to 0. Okay. And then I iterate as follows. And basically update xi to be the old xi minus vi times, now this expression looks exactly like what we had here, right? This is exactly this type of operation. Basically have normalized the length of the vector, and here I'm taking the inner product between the current gradient and this new basis function vector. So this is exactly the type of expansion that we will get for solving a linear system. The second thing that I'm doing is I'm computing, okay, now this is obviously wrong. Sorry, this is correct, so the new gradient is k times xi plus 1 minus L. I'm just computing the new gradient. I'm writing that out in this form because later on, when we have non-quadratic functions, you can actually still make those iterations work, where now you have just true gradients plugged in as opposed to the terms of a quadratic. And then this vector vi plus 1, I'm now performing a small modification on the gradient in such a way that these vectors will all be orthogonal. And we're actually going to show all of this. We're going to show that this is the best update you can perform in this V space, and that this update on the new gradient will give me yet another k-orthogonal vector. And of course I increment my counter until the gradient goes away. In practice, if you have a nonlinear function rather than a quadratic one, just a general nonlinear convex function, you would run a few conjugate gradient steps and then restart. Okay, so let's first actually prove this deflation property. By the way, if anybody has questions, raise your hands, because if you don't ask, I will assume that you understand this stuff.
So V is a Gram-Smith of trees?
So basically the VIs are essentially what I get through Gram-Schmidt in this k-orthogonal system. That's exactly what it is. Yep?
Any intuition about what this looks like visually?
So what visually happens is, okay, so basically put yourself visually in a distorted space where, things are rescaled in some ellipsoid, right? So, okay, that's...
One thing to look at.
Okay, so maybe, okay, so if my space is all homogeneous, then walls look like so. Now, if my space isn't homogeneous, because I've distorted things in the form of an ellipsoid, first of all, I get actually meaningful preferred directions. Secondly, well, lengths are different in that space. So basically, put yourself into that space where distances here are shorter than distances here. Sorry, the other way around. But basically, this space is now distorted, and now what you're doing is in that space, you're trying to find an orthogonal system of vectors. And, that's basically, you're just running Gram-Schmidt in a different space. That's the only real difference to what we're doing otherwise. Now, let's actually prove this property. So the first thing is, I'm assuming that those VIs are actually k-orthogonal, and then I'm going to show that at each step what I'm projecting out is the best thing I can do. Now, in order to show this, the only stuff that I need to do is I need to show that, if I compute the next gradient, that this is orthogonal to all vj's, all of those basis vectors less than the ith one. Because if I can, but that part actually is, no, sorry, that is straightforward. That's straightforward because the only thing that we did on our gradient, right? This vector only got updated twice on vi. These are k orthogonal. So whatever happened here for j less than I, it's obvious. But for j equals I, let's actually write it out explicitly. So vi transpose gi plus 1. That's vi transpose. Now gi plus 1 is just k times xi minus l minus whatever update we perform. So that's k times vi times gi transpose vi, right? Now, let's just actually plug terms back in. This was our old gradient, so that was vi transpose gi, right? Minus, and then here we have vi transpose k vi times gi transpose vi divided by vi transpose k vi. Now these two terms cancel out, and I get vi transpose gi minus vi transpose gi, which equals 0.
And the L go?
What?
Why the L is orthogonal to the?
So, well, that's just my gradient. So the gradient is, well, the gradient of my objective
Oh,
function.
yeah.
So it's, 1/2 x transpose kx minus L transpose x plus some constant c. And so this is my old gradient. And since by induction it held for, the gradient at I, we've therefore established that everything is, so for this you don't even need that property yet, but for this it's just 0. For smaller j, it's just a consequence that we have a k-orthogonal system. Because our updates in X are performed only in a space that is already k-orthogonal, so if we then push that vector through k again and take in the products, things go away. So what this shows is that essentially for this new gradient, there is no direction in which I could have moved otherwise to reduce things. And that's exactly where I get orthogonality. Right, so this is basically just your first order condition. So think of it this way. Here, then, at this point, my gradient is orthogonal to the previous update. There's nothing else I could have improved, so the next step must be orthogonal, except that it's all distorted by k. K orthogonality itself, what you do is you just work through the algebra. Okay, so xi plus 1 is xi minus vi, take this stuff up here. And this is our new gradient, right? gi plus 1 is k xi plus 1 minus l. Now we can write vi plus 1 as this gradient plus the correction. Right? That's exactly how our recursion looks like. And now we just need to check that this I plus first vector is k orthogonal to all the vi's, all the vj's. So if vj transpose k vi plus 1 is minus vj transpose k gi plus, and now here we have this entire correction. Now this was k orthogonal by our update that we picked before. And for this, well, we have vj transpose k vi. Now, since this was orthogonal already by our induction assumption, this needs to vanish anyway. So we basically have this term to be 0 because we perform the deflation step, and this to be 0 by our induction assumption. When you pull those two arguments together, you get exactly that. This gives you the conditions under which conjugate gradient descent will do something useful. Now, why is it a good method? Well, essentially what we're doing is we first start off by computing the gradient. So the first step is basically a gradient descent step. That's good. However, what we then do is we basically feed that vector back into K again. So we essentially get powers of our state vector with, adorned with K. Now, if you think about it, it's the leading eigenvalues in K, so the largest eigenvalues that will be most dominant in the subspace that you're going to get. Because those are the ones that will be expanded the most, whereas the very small eigenvalues, well, that subspace will not really show up so much. So if you think about it in pictures, okay, let's say that third dimension here were really small. It's kind of hard to draw, but basically for the first two dimensions, you're probably going to get vectors that point somewhere around here, and not so much into that third dimension. Now those two vectors will fairly well span the space, and those two dimensions where interesting stuff happens. And so you're going to get a very quick reduction in the objective function very early on. At each step you only perform one gradient computation. Now, if I don't have a quadratic function, it actually turns out that you can still essentially play the same trick. And the algorithm then just gets a different name. It's called Fletcher-Reeves or Pollack-Riviere. And the key difference is that you use slightly different coefficients for what it means to be a K orthogonal. So these were our generic coefficients. If you look at the iteration that we had, this is basically what you can derive. That was basically for how far I could update, and this is to keep the vectors orthogonal. Now Fletcher-Reeves basically replaces this first step with a line search, and then you can actually show that this term in the quadratic case is equivalent to GI plus 1 transpose GI plus 1 divided by GI transpose GI. And they just generalize accordingly. That's Fletcher-Reeves. And, well, Pollack-Riviere does the same thing, except that they correct the gradient. And you can do that because you can assume that these gradients are actually orthogonal to each other, so this goes away. But in a quadratic case, but in a non-quadratic case, of course, they don't go away. So, and you can make some convergence argument why this is a good idea. So, if you ever hear about Fletcher-Reeves or Pollack-Riviere for solving general convex functions, don't be scared. That's really what they're doing. This is essentially a fancy version of, conjugate gradient descent. Now, CG, or conjugate gradient descent, so this method is good whenever it's cheap to compute a matrix vector product. There are some cases when this is a really good idea. Does somebody have an idea where this occurs in practice?
Sparse.
When the matrix is sparse. Okay. In which cases would a matrix be sparse?
0 ones.
Yeah, that's true if I have a lot of zeros, but can you think of an application when this would happen?
N-gram word model.
Perfect. So for natural language processing, if I have particular strings, then most of the n-gram features are going to be zero anyway. So there's only a very few non-zeros. In which case, under certain conditions, you can actually perform this matrix vector multiplication very efficiently. Who has used Facebook today? Okay, good, fair number. So another case where this is very efficient. Graphs. Basically, they have exactly that structure of many zeros and a small number of ones. Or also web graphs have that property, except that you need to modify them in some cases a little bit to be positive semi-definite. Otherwise, you don't get the nice convex optimization problem. But that's basically some of the cases where this is quite effective. Sometimes also regulatory networks in bioinformatics might have this property.
But in that case, if you have a big matrix, so the upper bound for this, the number of steps is converged to the true thing is bounded by the size of the matrix, right?
Correct. In general, the number of iterations is number of dimensions of the matrix. Now, in general, I don't win over just a simple matrix inversion. So it's still cubic. So it's because it's n by n for a matrix vector multiplication. And then I have n of those operations. However, if I have only a very small number of non-zeros, let's say that the number of non-zeros is something like n log n as opposed to n squared, then my algorithm already becomes order n squared log n. So I have 1. Does somebody else know yet another case where I might even have a dense matrix where CG is really fast? Any idea? So remember before what I talked about the eigenvalues?
Low rank matrix.
Exactly. So if I have a matrix that's low rank, that's truly low rank, I only have to take as many steps as this matrix has rank. If the matrix is approximately low rank, I will probably be almost done after as many steps as the meaningful low rank portion of the matrix has. There are a couple of randomized algorithms which allow you to do similar operations to this in just 1 or 2 passes through the matrix. So they essentially pull out the meaningful singular vector singular value part in just 1 or 2 matrix multiplications. So if you're interested in that work, there is a beautiful paper by Alke, Martinson, and Trop. I think there's only one paper of about 50-60 pages linked by those 3 authors. And it's beautiful in 3 aspects. First of all, it's really extremely well written. Secondly, the practical algorithm is very simple and easy to use. Third, there are actually very nice concentration of measure inequalities for matrices in there. They are not easy reading, but they're also very beautiful. Okay. Now, if I have a general possibly non-convex function, but it's continuous, then this is effectively the method that you want to use, BFGS. This is sort of the, well, does it all miracle cure for most continuous optimization problems. At least as right now there is no standard go-to method that would work a lot better than BFGS or some variants of that. Yeah, those are the cool guys. I mean, I suppose in the 70s that's what you looked like. And there are lots of variants of that, and I'll tell you more of them in a moment. But basically, if you do something like a function minimizer in MATLAB or also in NumPy or SciPy, this is probably the solver that you would be using. And in general, I strongly advise you against implementing your own minimization algorithm if you can avoid it. Because there are a lot of fine-tuning details and safety aspects basically to make sure that things don't diverge and so on, that you're probably going to forget if you implement it yourself, that the people who've written those packages have probably thought of. A couple of exceptions, and you may probably actually want to look into the code. So like there's some very supposedly large-scale machine learning toolkit like Mahout. If you look at some of the algorithms, there are just holes in it. So it's a good idea to look at the code to make sure it's doing the obviously right thing. However, after that, try avoiding doing the work on your own. Anyway, so what's the basic idea of BFGS? So the idea is to have something like a Newton method, where you want to get this update. So this is essentially is something like a quadratic matrix. So this is my gradient. Now, the point is, how do we actually get this quadratic matrix, and then how do we update? Well, the first thing is simple. I mean, I basically perform a line search in this update direction. So this looks like a Newton method, but this BI is going to be computed in a funny way. And what we do is we basically assume that this B matrix doesn't change very much as I take another step. Now why is this advantageous? Because if I had a factorization for B before and I only perform a rank 2 modification, I can very quickly get the factorization for this new matrix. If this looks surprising to you that you can do this, you should pick up a basic linear algebra tutorial, numerical linear algebra tutorial, and look it up. This is one of those really extremely useful facts of numerical analysis that you really need to know. You're going to save yourself a lot of work if you do. So basically, low rank modifications of matrices, which you've already factorized, you can solve very efficiently again. So, in other words, if I have a factorization of, let's say, this matrix in the form of product of two triangular matrices, which is all I need in order to solve this linear system of equation in quadratic time. Has somebody who has not seen that type of trick before? So, who has seen Cholesky factorizations before? Okay, good. So I'm assuming that if you haven't seen that, read up on it. In any case, so if you can factorize a matrix like this, then if I take this matrix and add a low rank object to it, times this plus that, then I can modify this factorization by maybe pulling some matrices out here, and then solve for this updated linear system of equation efficiently too. And the cost for these updates is a lot less than computing everything from scratch again. So that's where you want to do it. Okay, so the requirement is that we say, well, our new, Hessian-like structure bi plus 1 should look like our old one, and I'm allowing for a rank 2 modification. And now what I'm going to do is I'm going to say, well, and this is sort of a backwards reasoning by arguing that, my Taylor expansion by using this matrix, should give me the difference between the gradients. Yeah. If I had a proper Taylor expansion, that's what would hold, right? It's basically, the Taylor expansion of the gradient is given by the second derivative of my objective function here times, the difference in the points where I evaluate. Well, plus some higher order terms. And I'm going to do a backwards reasoning here on this. And then if you do a little bit of algebra, you can see that this is the update for BI. That's really useful because now, these operations can possibly be done fairly cheaply. And then also the factorization for BI can be done efficiently. Because at the end of the day, up here I need to invert this. We're not going to go through the convergence proof and all that, but essentially there are lots of variants of this. So if you use something like tau, the toolkit for advanced optimization, or if you use MATLAB or NumPy or whatever, they use some version of this. There are online variants of that solver, there are memory limited versions, so there's a lot more work that was then built on this, but the original BFGS paper is really what started it all. So, in case of doubt, use this. If you have a convex problem, you're probably better off using something else, but if the problem is non-convex in general, well, that's what you want to do. Any questions so far? No? Okay.
I have a question.
Yes?
So in terms of parallelizing this?
This is really hard. Yes. So you're absolutely right. This is a problem. So tau tries to do a little bit of that. So tau is a big optimization toolkit beast, and it has a fairly steep learning curve. It tries to parallelize some parts of it, and in general, it's pretty good with, let's say, matrix-matrix or matrix-vector operations where you have parts of the matrices in different places. So the Argonne National Laboratory, for instance, the guys there contributing to tau. So it's one of those hardcore numerical analysis tools. It's very high quality code. Might be Fortran to some extent, but it's still high quality code. Parallelizing some of these updates is hard. So if you go back to this, for instance, this matrix inversion, that can be a problem unless you do some very clever tricks with layout. This rank 2 update, for basically which you get through Sherman, Morris, and Woodbury, can be messy to some extent. So there are a couple of issues in this context, but I mean you can work through it, and at the end of the day, you don't want to do it yourself. So now let's have a look at some constraint convex problems. So now this is a general convex constraint optimization problem. I want to minimize some function f of x under the constraint that ci of x less equal than 0 for all I. And so these are some common constraints, and each of those has spawned an entire industry of applications, optimization algorithms, codes that go with it, and proofs. And okay, it's probably a little bit late in the game to, try to get tenure with that, but there was a lot of great work that came essentially out of the insight that a lot of things in engineering can be viewed as such optimization problems. So the simplest constraints are linear inequality constraints, which basically just means you impose a hyperplane constraint. So in other words, you're saying that your parameter should sit on one side of the space. That's basically what w dot x plus b greater or equal than, or in this case less equal than 0 says. Now why is this interesting? Because I can have several of those constraints. So another constraint might do that, right? Rules out that space. So now I already have an interesting space. Now I could have a third constraint with a third color which I may not have. We have red. That might constrain the space here. And now I've constructed a triangle by using 3 linear inequalities. So that's a fairly nice way of describing domains. Another one is quadratic cone constraints. So this is basically a way how you can write out ellipsoids or then entire cones. So if I have, 1/2 q transpose x, x transpose qx plus b transpose x less equal than c, this is a quadratic, that gives me immediately, if I just have that, that will give me an ellipsoid centered at the origin, and then depending on how c and b are chosen, it will give me either a cone or the empty set, or possibly just an ellipsoid again. And then there are those semi-definite constraints, and they're a little bit more tricky to see. They are basically expressed in terms of matrices. So there I'm saying the linear combination of a couple of matrices needs to be positive semi-definite. Okay. And you can check at some point for yourself that this actually gives me a convex constraint. In other words, that the linear combination of 2 positive semi-definite matrices is again a positive semi-definite matrix. Does somebody have an idea how to do this?
To the eigenvalues?
You could go for the eigenvalues, but would that help? Let's see. If they commute, that's true. If they commute, that's the solution of the problem. So I have some matrices A and B. They're both positive semi-definite. Now, I need to show that lambda A plus 1 minus lambda B
Just do by definition, I guess.
is also positive semi-definite. So, exactly, it follows immediately by just, plugging in x transposed x, this matrix in x here. So we have x transposed, this entire beast, x, Now, things are positive semi-definite for this term here. Things are positive semi-definite for this term here. And so since I'm taking a linear combination, I'm safe. And so you can show that this actually defines a nice cone. It's a cone because if I take any element from that set and scale it up, it's still in the set. So that's a nice property in addition to just convexity. Question? Yeah?
Just to be sure, is the x's there, do they need to be non-negative? Semi-definite history?
They may or may not have to be non-negative. So, okay, let me give you a simple example. Suppose that M naught is the identity matrix. And maybe I just have another matrix here, M1, which is also the identity matrix. Then xi could actually be, you know, as long as it's greater or equal than -1, this is positive semi-definite. So you can get very non-trivial constraints on the xi's by playing with the eigenvalues. So for about maybe 5 years, there was a sizable industry in machine learning in the learning the kernels context, where people essentially played with those constraints and found interesting optimization problems and solvers. So this has now been supplanted by structured sparsity, and people prove interesting things there. Question here?
Yeah, what's an example of like a semi-definite constraint in practice?
Okay, so one constraint that we might have quite often in the context of kernel methods, and I mean we haven't introduced kernels yet, but basically kernels are functions that will give you matrices that have all eigenvalues greater or equal than 0. You could ask, you know, maybe a linear combination of some of those kernels might actually be more meaningful than a single kernel. And you might not exactly know how you should weigh various terms, so you can actually optimize over that. So that's one example. Another example is, let's say I have a covariance matrix, and for whatever reason I only observe parts of it. Now, since it is a covariance matrix, I know that that matrix has to be positive semi-definite. So then the question becomes, fill in the remaining entries of the matrix, so it's a matrix completion problem, under the constraint that the matrix remains positive semi-definite. Another example is one where I want to learn graphical models. So, who has taken Mike's and Martin's class last semester? Okay, almost, yeah, half of the audience, good. So, basically, at some point you might, so there you probably remember that the inverse covariance matrix in a Gaussian gives you the connectivity structure of a corresponding graph in a Gaussian graphical model, right? And so you might want to ask, well, can I find a sparse Gaussian graphical model that, you know, actually fits Medata fairly well? And so you will have some likelihood term expressed in terms of this, you know, this covariance matrix of your Gaussian graphical model, and you will actually want to get some sparsity. So you have a positive semi-definite constraint because you need to make sure all eigenvalues remain non-negative, and you will have an additional sparsity constraint, and then you can do interesting convex optimization procedures. So Alexandre Descoumont and yeah, I think also Mike Jordan and Laurent Elgavi and a few other people have written a couple of very nice papers on that context. So look up their papers. This is quite nice. Question for the audience. Can somebody tell me why linear constraints are a special case of this? So basically linear equality constraints. No, for here, basically how can I make this into a linear constraint, equality constraint? Because we have an inequality here. It's a trick question almost, right? Because basically what I do is I create, you know, ax plus b greater or equal than 0 and ax plus b less equal than 0. And by those two inequalities, the only solution is an equality. So that's why I didn't really deal with that case specifically. So, yep.
Could you explain again how these semi-definite constraints look like? You provided some information with code.
Honestly, I think my imagination fails me here as well, and I'm not sure I'm a very good person to draw those spaces I have not a very good idea of on the whiteboard. Possibly the Boyd and Vandenberg book might have 1 or 2 sketches, but these are very generic convex bodies that you can get. So basically think of any convex, shape that has, various, smooth surfaces and maybe a couple of, singularities. And you will probably be able to transform that into a linear matrix inequality. As a matter of fact, this is something that, Stephen Boyd has been doing with tremendous success in a lot of engineering disciplines. So he looked at various optimization problems and used a lot of ingenuity and, of course, also theory, and said, well, by the way, this is a semi-definite programming constraint. So now we can use convex optimization to solve this specific problem. And that works for a surprisingly large number of problems. So if you want to know, examples of that, really have a look at his papers or his book, and there's plenty of applications in there. So it's actually very surprising and amazing what you can do there. So in our context, we're going to do a small preview, namely we're going to look at support vector machines. And we will discuss that in a lot more detail when we get to the support vector section, which will be after the optimization. But I just want to put things a little bit into context to make sure that we all know what we are talking about. So for an SVM, basically in its simplest form, so this is the version from the 60s, this is Watnick and Lerner, I think 1963, and they didn't call it support vectors, but they called it generalized portrait. Okay. I'm not sure why, but that's what they did. Maybe it sounded nice in Russian. So what you have some points, let's say the negative and the positive points. You want to separate them with a hyperplane. And for the moment, I'm assuming that it's actually possible to separate them. Then, there are lots of hyperplanes that I could draw across it, and we'll actually get to that when we look at the perceptron. But the hyperplane that I'm going to try and find is the one that has the largest margin between the two sets. Now, what you can do is, of course, there has to be one point that sits on that side of the margin and another point that sits on the other side. Because if there were none on one of those sides, I could just expand the margin further. Right? And without loss of generality, you can say that w dot x1 plus b at one side has to be 1, and for some other point it has to be minus 1. Because I can always scale w and b to satisfy this. Right? So therefore, if I just subtract those two equations from each other, I get w dot x1 minus x2 plus b, well actually that b goes away, typo, equals 2. And now, if I do that, well, I can just, divide by the length of w. I basically divide that out here, because that now gives me the width of that hyperplane, of that margin. So I basically take that distance vector, x1 minus x2, take its inner product with the unit vector normal to the hyperplane, and that's the side of the margin. Right? That's what happens. And that gives me 2 over the norm of w. So in other words, I want to maximize 2 over the norm of w under the constraint that all the negatives stay on the left and all the positives stay on the right. Now, maximizing the norm, 2 over the norm of w is the same thing as minimizing 1/2 norm of w squared. Right? So we minimize norm of w squared over 2, as opposed to maximizing 2 over the norm of w. Nothing has changed. Now, for all the negatives, we need to ensure that x dot w plus b is less equal than minus 1 for the negatives. For the positives, we need to ensure that xi dot w plus b is greater or equal than 1. Now that's kind of awkward to have to carry this thing around with us. So what we can just do is we can multiply this with minus 1 here. So again, minus 1 times this equation here is greater or equal than 1. Now that's exactly, the label being 1 or minus 1 of the classification problem, and we get this constraint here. So this is a quadratic program. It's a quadratic program because we have linear constraints and a quadratic objective function. Pardon? No, it's not a linear program. It has linear constraints. That would be okay. But the objective function has a square in it. No, actually, the objective function is just as important. So if you had a linear objective with quadratic constraint, or quadratic objective with linear constraints, you can actually play some games and mix things. And so as soon as you have a single quadratic term occurring here, the problem gets quite a bit harder. And I'll show you how to solve it.
Can I ask you a question before? I mean, the b is fixed from the beginning, right?
No, b is not fixed. B is another variable, so that's why we optimize over w and b. Let's just make b go away by subtracting them from each other.
Okay.
So, and that b is actually going to give us a lot of headache. So, it's an important enough problem that some people many years ago thought they should be writing a paper which aimed to have the shortest title called B. To my knowledge, it didn't fare so well. So I don't know whether it got published in the end, but so how do we actually solve this thing? So what I'm going to show you now is how the entire theory of Lagrange functions and Lagrange multipliers and so on works. So those of you who've seen this before can take a nap or read something interesting, but actually we might just take a short break, maybe 5 minutes or so, and then we get to the Lagrange functions.